Hello everyone. In this video, we are going to discuss about electronic configuration of elements and the periodic table from the chapter 3 classification of elements and periodicity in properties class 11 chemistry. See, we will be discussing the electronic configuration in periods as well as the electronic configuration in group, that is group-wise electronic configuration. You see, an electron in an atom that is actually characterized by a set of four quantum numbers: principal quantum number, azimuthal quantum number, orbital magnetic quantum number, spin quantum number. Spin quantum number ms, that can also be represented like that. Okay, ms. And you see, the value of n, that is principal quantum number, that actually defines the main energy level known as the shell, that is K shell, L shell, M, N. The filling of electrons into different subshells, SPDF, also referred to as orbitals, SPDF, in an atom. The distribution of electrons into orbitals of an atom, that is actually called as its electronic configuration. See, an element's location in the periodic table, that actually refers to the quantum numbers of the last orbital filled. So, by looking at the quantum number of the last orbital filled, we can determine the location of an element in the periodic table. So, let us see the electronic configuration in periods. You see, the period actually indicates the value of n, that is the principal quantum number, for the outermost or valence shell. The period indicates the value of principal quantum number n for the outermost shell or the valence shell. See, when we consider the elements in the first period, we have only two elements in the first period, that is hydrogen and helium. Hydrogen, its atomic number is 1, and for helium, its atomic number is 2. So, there are only two elements in the first period, hydrogen and helium. See, the order of energies of the orbital is like 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. That is only after 3d is filled, the electron goes to the 4p orbitals, then 5s, 4d, etc. So, you see, for hydrogen, its atomic number is 1, so electronic configuration will be 1s1. Okay, then for helium, its electronic configuration will be 1s2. You see, n is equal to 1, that means the shell is K shell, which is the first shell. See, the maximum number of electrons S subshell can fit into is 2. So, the lowest level of 1s is completely filled for first period elements, and the first shell K is completed. So, here the highest value of n is 2 for the outermost shell. Okay, not 2, it is actually 1. The highest value of n for the outermost shell is actually 1. So, here you see hydrogen. For hydrogen, the highest value of n for the outermost shell is 1. For helium also it is 1. So, for both hydrogen and helium, they are actually the first period elements. You see, the number of elements in each period is twice the number of atomic orbitals available in the energy level that is being filled. So, in the first period, the only orbital available is the s orbital. So, only one orbital is there. So, number of elements will be twice of 1. Twice of 1 means 1 into 2, which is equal to 2. So, only 2 elements are there in the first period, which are hydrogen and helium. That is, the number of elements in the first period will be equal to twice the number of orbitals available for the first period. So, only one s orbital is available. No, only one orbital is available, that is s. So, the number of orbitals in the first period will be twice of 1, that is 2. The two elements are hydrogen and helium. Now, let us consider the second period of the periodic table. You see, the second period starts with lithium and ends with neon. See, lithium has an atomic number 3 and neon has an atomic number 10. And how many elements are there from lithium to neon? 1, 2, 3, 4, 5, 6, 7, 8. 8 elements are there in the second period. So you see the second period of the periodic table starts with lithium with atomic number 3 and ends with neon with atomic number 10. So the electronic configuration of lithium will be 1s2 2s1. So 2 plus 1 3 electrons. For neon it will be 1s2 2s2 2p6. So 6 plus 2 8 plus 2 10. Okay, so here in the case of lithium you see the third electron, that is 1s2, so 1s orbital is completely filled. Then the third electron enters the 2s orbital. That is starting from the next element, that is after lithium we have boron, which has an atomic number 5 here in the period. So you see starting from the next element boron, the 2p orbitals are start to be filled. Okay, and the 2p orbital will be completely filled at neon. And the L shell is completely filled. Here you see, for these elements, the highest value of N is 2. Okay, so here the highest value of N is 2. For boron or any other element is in this period, the highest value of N will be 2. So these elements are in the second period. Because the highest value of N is 2, so these are second period elements. Now you see the atomic orbitals available here are the s orbital and the p orbital. So s orbital and p orbitals are available here for the second period elements. See, we know that p orbital means actually we have px, py and pz orbitals. So the number of orbitals available here for the second period elements are actually 1 s orbital, then 3 p orbitals. So total 4 orbitals are available. So the number of elements available in the second period will be what? Number of elements available in the second period will be equal to twice of this value. Okay, twice of number of orbitals available. Number of orbitals available for the second period elements are 4. It is actually 4. So twice of 4 means it is actually equal to 8. So there are 8 elements in the second period as we have discussed earlier. Okay. Now, let us consider the third period elements. It starts from sodium. Okay, then here we have aluminium, silicon, phosphorus, sulfur, etc. Then it ends with argon. Okay, and how many elements are there in the third period? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 elements in the third period. That is, you see, the third period starts with sodium and ends with argon. See, sodium, its atomic number is 11. So, electronic configuration will be 1s2, 2s2, 2p6, 3s1. So, 2 plus 2, 4, 4 plus 6, 10, 10 plus 1, 11. Similarly, the electronic configuration of argon will be, see, its atomic number is 18. So, 1s2, 2s2, 2p6, 3s2, 3p6. So, here you see, you can consider any other element in between this sodium and argon. The highest value of N will be 3. For all third period elements, the highest value of N will be 3. So, these elements from sodium to argon are included in the third period. Okay, and you see how many atomic orbitals are available for the third period elements? S orbital is available and p orbital is available. P means px, py and pz. So total 1, 2, 3, 4. 4 atomic orbitals are available for the third group elements. So twice of 4 means 4 into 2, which is equal to 8. So the number of elements in the third period will be equal to 8. Okay. Now, when you look at the fourth period of elements, you see the fourth period starts with potassium and ends with krypton. Okay, the atomic number of potassium is 19 and for krypton it is 36. And you see how many elements are there in the fourth period? From potassium to krypton, actually there are 18 elements in the fourth period. So you see the fourth period starts from potassium. Its atomic number is 19, so electronic configuration will be like this. And it ends with krypton, whose atomic number is 36. Its electronic configuration would be like this. So here you see, you can consider any other element in between potassium and krypton. the highest value of N will be, for any other element between krypton and potassium, the highest value of N will be 4. The principal quantum number N, its highest value is 4 here. So these elements from potassium to krypton are in the fourth period. Okay, now you see what is the number of atomic orbitals available in the fourth period. See, S orbital is available, P is available, and D is available. So the orbitals available here are S, P, and D. We know that S has only one orbital S, but P has actually Px, Py, and Pz. 3 orbitals are there in P. And when you consider the D orbital, actually there are 5 orbitals, degenerate orbitals, degenerate energy levels for D orbital. That is dxy, dxz, dyz, then dx square, y square, then dz square. So how many atomic orbitals are available in the fourth period? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 1 s orbital, 3 p orbitals, and 5 d orbitals. So total 9 orbitals are available in the fourth period elements. So what will be the number of elements? Twice of this atomic orbitals available, that is 9 into 2, which is 18 elements are there in the fourth period. Okay. And you may note that before 4p orbitals are filled, filling up of 3d orbitals becomes energetically favorable, and we come across the so-called 3d transition series of elements. So what is the transition, or what are there, which are the elements in the transition series of elements? Let us see that. That is before the filling up of 4p orbitals, the filling up of 3d orbitals becomes energetically favorable, and we get the 3d transition series of elements. So you see, in the fourth period, these yellow colored one now from scandium to zinc, these are the 3d transition series. Okay, these are the 3d transition series elements from scandium to zinc. Okay, that is the transition series in the fourth period. Across the fourth period, the transition series starts from scandium and it ends with zinc in the fourth period. Okay, so these are actually the 3d transition series elements. See, for scandium, its atomic number is 21. See, the transition series starts from scandium. Okay, so for scandium, its atomic number is 21. So electronic configuration would be like this: 4s2 3d1, outermost one. Then for zinc, it is 30 atomic number. So its electronic configuration would be like this. Okay, that is, you see, the 3d orbitals start to fill from scandium, 3d1 here. So it starts to fill from scandium. And the 3d orbitals get completely filled at zinc, because you see 3d10, the maximum number of electrons possible in the d shell is d orbital is 10. So the orbitals start to fill from scandium, 3d1, and it gets completely filled at zinc. Here you see 3d10. Okay, so that is why these elements from scandium to zinc are called as 3d transition series elements. And you see, the fourth period starts from potassium and it ends with krypton. Okay, with the filling up of 4p orbitals. See, the fourth period starts from potassium, ends with krypton. You see, the fourth period ends at krypton with the filling up of 4p orbitals, because you see the maximum number of electrons possible in a p orbital is 6, so 4p orbital is completely filled here. So the fourth period contains the 3d transition series and the other elements as well, and all together we have 18 elements. Now let us consider the fifth period. It begins with rubidium. Its atomic number is 37 and it contains 4d transition series starting at yttrium. Please excuse me for the pronunciation. And this fifth period ends at xenon with the filling up of 5p orbitals. So when you consider the fifth period, it begins from rubidium. it contains the 4D transition series, starts from yttrium to cadmium. Then this fifth period ends at xenon with the filling up of 5p orbitals. So fifth period begins with rubidium. Its atomic number is 37. So its electronic configuration would be like this. It ends at xenon. Its atomic number is 54. So its electronic configuration would be like this. So here the highest value of N is 5. So these elements are in the fifth period because its highest principal quantum number is 5. See, the fifth period ends at xenon with the filling up of 5p orbitals, because when you consider the 5p orbital, the maximum number of electrons possible in the p orbital is 6. So the fifth period ends at xenon with the filling up of 5p orbitals. And you see how many atomic orbitals are available in the fifth period. S orbital is available, p orbital is available, and d orbital is available. So total 1 s is there, 3 p are there, and 5 d orbitals are available. 1 s. So total 5 plus 3, 8 plus 9 orbitals are available. So number of elements would be twice of this atomic orbitals. That is, total 18 elements are available in the fifth period. Okay. Now let us consider the sixth period of this periodic table. See, the sixth period begins with cesium. Okay, and it ends at radon. See, the sixth period actually contains 32 elements because 18 elements are here and 14 elements are separately given here just below the main body of the periodic table. So 14 plus 18, total 32 elements are there in the sixth period. See, the filling up of 4f orbitals, that actually begins with cerium. Its atomic number is 58. So the filling up of 4f orbitals, that actually begins with cerium, and the filling up of 4f orbitals ends at lutetium, because here we have 4f 14. The maximum number of electrons possible in f orbital is 14. So f orbitals, 4f orbital is completely filled here for lutetium. So the filling up of 4f orbitals begins with cerium and ends at lutetium. This is also a part of the sixth period. And you see, this actually gives the 4f inner transition series, which is actually called as lanthanoid series. That is, the filling up of 4f orbitals begins with cerium and ends at lutetium to give the 4f inner transition series, which is actually called as lanthanoid series. See, the 4f inner transition series refers to the series of elements in which the 4f orbitals are being filled. This series actually includes the lanthanoids and also known as rare earth elements. See, the series which includes lanthanoids are actually called as rare earth elements. That is, lanthanoids are also called as rare earth elements. Now let us see the list of elements in the 4f inner transition series. Actually, here we have lanthanum. Please excuse me for the pronunciation, lanthanum. There are no electrons in the 4f orbital actually, so 4f0. For cerium, then you know the 4f inner transition series elements are cerium. Okay, then praseodymium, neodymium, promethium, samarium. Okay, then europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. Please excuse me for the pronunciation. So these are actually the 4f inner transition series. Now, when we consider the seventh period of elements, the seventh period is actually similar to the sixth period with the successive filling up of the 7s, 5f, 6d and 7p orbitals. So here you see, here we have we have these elements in the seventh period. This also belongs to the seventh period. You see, the seventh period elements actually includes most of the man-made radioactive elements. See, the 7th period starts with francium and it ends with an element organozone. This element belongs to the noble gas family. You see, the filling up of 5f orbitals starts after actinium and it gives the 5f inner transition series, and these are actually called as actinoid series. So you see, for thorium 5f0, then palladium, uranium, neptunium, okay, 5f1, 5f2, 5f3, 5f4, like that. So you see, the filling up of 5f orbitals starts after actinium. That is, after actinium we have these elements, okay, till atomic number 103, lawrencium. Then after lawrencium we have atomic number 104 RF element here. So this series of elements, this is actually called as actinoid series. 5f inner transition series, which is also called as actinoid series. You see, the 5f inner transition series refers to the series of elements in which the 5f orbitals are being filled. That is, it starts from here, and when it reaches lawrencium, you see 5f14. So the 5f orbital is completely filled here. See, this series includes actinium. So for actinium 5f0, then thorium, we have nobelium here, we have lawrencium here. And you see, the 4f inner transition series and 5f inner transition series, and these elements, the series of these elements are placed separately in the periodic table to maintain its structure and to preserve the principle of classification by keeping the elements with similar properties in a single column. Now, let us discuss about group-wise electronic configurations. See, elements in the same vertical column or group have similar valence shell electronic configurations. The same number of electrons in the outer orbitals and similar properties. For example, if you consider the group 1 elements, this is the group 1 elements, lithium, sodium, potassium, rubidium, cesium and francium. These are the group 1 elements. These are actually also called as alkali elements or alkali metals. And you see, when you consider lithium, its outer electronic configuration is given here 2s1. For sodium it is 3s1. Okay, then for potassium it is 4s1. Rubidium 5s1. For francium it is 7s1. So you see, for all the group 1 elements, all have like ns1 valence shell electronic configuration. N can be 1, 2, 3, 1s1, 2s1, 4s1, like that. So the outermost, for all the group 1 elements, the outermost orbital has only one electron. 3s1, 4s1, 5s1, outermost orbital has only one electron. Okay, so all these are placed in group 1. And when you consider group 2 elements, beryllium, magnesium, calcium, okay, when you consider group 2 elements, see the outermost orbital, it has 2 electrons. 2s2, 3s2, 4s2, 5s2. So the outermost orbital of all these elements have 2 electrons. So that is why all these elements are placed in group 2 of the periodic table. Similarly, when you consider group 3 elements, outermost orbital, you see its electronic configuration 3d1, 4s2. So 1 plus 2, 3. Okay, 3 electrons are there in the outer orbital. So group 3. All these elements are in group 3, then group 4, 5, etc. So everything is the same like that. But when you come to this boron family, group 13, outermost orbital has, you see, 2s2, 2p1, 3s2, 3p1, 4s2, 4p1. So 2 plus 1, 3. Outermost orbital has 3 electrons in. From, in boron family, outermost orbital, that is in group 13, outermost orbital has 3 elements. So from here you have to add 10 with the outermost number of electrons to get the group number. So here 3, so 3 plus 10, 13, group 13. Similarly, when you consider the carbon family, group 14, outermost configuration 2s2, 2p2, 3s2, 3p2, 4s2, 4p2. So number of electrons in the outermost orbital is 2 plus 2, 4. So 4 plus 10, 14. So group 14. Okay, and similarly for group 15, 16, 17 and 18. And group 18, you see, except helium, all other elements, neon, argon, krypton, you see 2s2, 2p6, 3s2, 3p6, 4s2, 4p6. the outermost orbital has 8 electrons. So 8 plus 10, 18, group number 18. But except helium, okay, because helium has only 2 electrons, so its electronic configuration is 1s2. So when you add, only 2 electrons are there in the outermost orbital. So when you add 10 plus 2, you will get actually 12, not 18. So except for helium, all other will follow the same thing. So you see, helium, it has unique properties and noble gas behavior. That is why it is placed along with the noble gas elements. Okay. So in this video, we have discussed about the electronic configuration of elements across the period as well as group-wise electronic configuration. I hope it is clear to you. Thank you.